Hi, in today's biochemistry bit section, we are going to describe a short concept video. The topic is basis of sickling in HbS. So to begin the basis for sickling in HbS, you need to know first what is HbS. It is nothing but it is a variant of hemoglobin which occurs because of a point mutation in hemoglobin, that is a single nucleotide change. A GAG is replaced by GUG. Instead of A, it is replaced by U. Okay. So what happens? This particular code codes for glutamic acid and this code codes for valine. So there is a amino acid substitution in the hemoglobin chain, where in the beta chain of hemoglobin, in the sixth position, glutamic acid amino acid is replaced by valine. Please remember, it is glutamic acid. Many of you confuse with glutamin. It is not glutamin, it is glutamic acid. A single amino acid substitution occurs. So what? Just an amino acid is going to change. What happens because of that amino acid change? Replacement of glutamic acid by valine. What is glutamic acid? It is a polar amino acid. Okay. Whereas valine is a non-polar amino acid. So because of this one particular property, where a polar amino acid gets replaced by a non-polar amino acid, there is a sticky hydrophobic contact point or sticky patch. This is called a sticky patch formation in the outer surface of the hemoglobin molecule. So this happens on the outer surface of the hemoglobin molecule where there is a sticky patch. Now, both normal hemoglobin variant and HbS contains a complementary sticky patch on the surface only when exposed in the deoxygenated state. So how does the sickling occurs? So this is a picture taken from the Harper's textbook. This explains the basis behind the sickle shape of RBCs in HbS. Okay. So on the top of the picture, you can see various variants, that is oxygenated form of normal hemoglobin, deoxygenated form of normal hemoglobin. I told you already, in the deoxygenated state on the normal hemoglobin also, you will have a complementary sticky patch, which is this triangle area which is left out. And this side you can see the oxygenated hemoglobin S. Hemoglobin S is a mutation in the beta chain. So you can see the color change in the beta chain, which is represented here. And this is a deoxygenated HbS. When deoxygenated, HbS also has a complementary sticky patch in the form of a triangle here. And this side, if you see, it actually has the sticky patch. The sticky patch is created because in the beta chain because of the replacement of amino acid glutamic acid by valine. Okay, so this is the red triangle sticky patch, and this side you have the complementary sticky patch. So what happens once they come together, they start aggregating together. You can see how all the deoxygenated hemoglobin S molecules have started aggregating because they have sticky patch on one side, they have a complementary sticky patch on the other side. So they get attached to each other and gets aggregated and it continues. Okay, but once your deoxy HbA comes, that will also attach because it has a complementary sticky patch, but it will stop the polymerization because it does not have a actual sticky patch. That is the red color triangle is missing in the normal hemoglobin A. Okay, so this is how polymerization occurs and there are aggregates of hemoglobin molecules formed. So now how polymerization of fibers leads to a change in shape of RBCs. So that is explained by this particular diagram, which is taken from the Leninger's textbook of biochemistry. Okay. So this is a normal HbA and this is the HbS. You can see there is a slight shape variation in the beta chain because of the mutation. So when there is a mutation, these hemoglobin S molecules, as I told you, when deoxygenated, they will start to aggregate with each other. We were seeing the aggregation in this particular picture. That is how it is seen as a whole in the hemoglobin structure. Okay. Interaction between the molecules will lead to kind of strand formation like this, and more strands will form and get aggregated together to form this fibers. Now hemoglobin S polymerizes like this to form long insoluble fibers, and that in turn more and more aggregates to form tubular fibers when there is constant hypoxia. So now these insoluble fibers of deoxygenated HbS will cause the deformed sickle shape of RBCs instead of the normal biconcave shape of RBCs.